I think she wants in. All right. That's true. Here we go. Dot product of vectors. So technically, there are two different ways to multiply vectors depending on the context that you're in and what you want to do with them. A dot product is one of them. The other way is called an outer product or a cross product. We're not going to talk about cross products. When you guys at some point get to Calculus 2, you'll get back, like I said, with the I's and the J's. You won't see that again probably till Calc 2 or linear algebra down the road. Cross products usually aren't used until you get to Calc 2 and Calc 3. Yeah, a little bit. Anyway, but it's not what you think. It's a different type of thing. Anyway, that being said, we're not going to worry about cross products. That really only works well in 3 dimensions, and we're not dealing with anything in 3 dimensions at the moment. A dot product, though, works for what we want to do with vectors in 2 dimensions. And so the method that you use to multiply using a dot product is as follows. So let's say that we've got this vector u, and I know my u looks like a mu, and that's just how I do it, and you're just going to have to put up with it. A mu? You guys know what mu is? Oh. It's a Greek letter that looks like a u. It has a little hitch at the beginning of it rather than just making the u. But anyway, that's just how I draw u's, and so if you don't like it, whatever. Let's say, and then we got vector v, who has components v1 and v2. Okay, and let's say I want to multiply those 2 vectors together using the dot product. So here's the process that one would take to do that. So the vector u times the vector w equals u1. What did I say? Oh, v. Oh my goodness. Okay, yeah. No, I got not a lot of sleep last night. Whew, okay. Write what I write, not what I say. So u1 v1 plus u2 v2. Yes, that's it. Got it. Yeah, a little bit. All right, so basically what you're going to do is you take the first component of each of the 2 vectors, multiply them together. The second 2 components of the 2 vectors, multiply those together, and then add the results of those, and that's going to be the dot product. Now, you can't. You can't. Because think about this for a second. I guess so. This is important, though. So when you guys added vectors, when you subtracted vectors, put your phone away, their answer was always another vector, right? We just did some problems like that out of your homework, right? When we added the 2, like with the plane and the wind, we added those 2 vectors together, we got a new vector as the answer, right? Which we could find the direction and magnitude and do all that stuff with. With a dot product, think about what you're getting. Each one of these components is just a number, right? You have a number times a number plus a number times a number. Ultimately, this is going to equal a number, right? Not a vector. That's what we're going to talk about, okay? So when you do a dot product of 2 vectors, the result is a number, put your phone away, not a vector, okay? So that's important. We're going to actually just write that down. Should I? Okay. You're welcome. Okay, so unlike all the other operations we've done so far, the result of a dot product is a number, not just another vector. Okay? Now, if I do a dot product and the answer comes out to like 2, the heck does that mean? Is it 2 what? My vector is, these 2 vectors multiply to 2. Awesome. So the number itself doesn't really have a lot of utility unless you put it in the context of something else. So if you're in the process of doing something else, the value of the dot product can tell you something about the vectors that you're looking at. But, well, give me a moment and I will show you. But the number itself doesn't so much have so much meaning for what you're doing. Okay? So, one example, this whole orthogonal thing. Dot products are involved with orthogonal vectors. Orthogonal vectors. There we go. Okay, orthogonal vectors is just a fancy way of saying there's two vectors that are perpendicular. That's all that is. It's a good question. Whoever came up with this, I would like to talk to them about that. But anyway, these are vectors that are perpendicular. And if we have two vectors that are perpendicular, there's something special that happens with their dot product. Okay? So let's take two vectors. Just hold on to that thought. Don't let the cat out of the bag if you think you got it. So let's come up with two vectors in component form that we know are definitely perpendicular to one another. Okay? So we're going to pick two orthogonal vectors real quick. Okay, perfect. So let's say we've got these two vectors, 1, 0, and 0, 1. So if we were on the coordinate plane, just so we're all clear, vector A would be like this, and vector B would be like that. Okay, definitely orthogonal. They're perpendicular. Okay, so do the dot product of A and B. If we follow the formula we talked about up top, we have to multiply the x's together, then multiply the y's together, and add those up. So 1 times 0 plus 0 times 1 would be the dot product of those two. So 0 plus 0 equals 0. All right, we'll do another problem here to kind of verify this to show you that it keeps working. But if you have vectors that are orthogonal, vectors that are perpendicular, their dot product is always 0. Okay? So orthogonal vectors have a dot product equal to 0. All right, so that's important because one part of the work I'm going to have you do is I'll give you two vectors and I'll say verify that these vectors are orthogonal, or show that these vectors are orthogonal or neither by doing a dot product, that sort of thing. So it's, I'm sorry, it'd be perpendicular, parallel, or neither. We'll talk a little bit about the parallel in a second here. But anyway, so two other vectors that we know are definitely perpendicular, because I've done this in the past and people are like, okay, well that came out to 0 just because you pick things on the axes and they have zeros in them, and you can't really do that. What if it was twisted? What if you had one vector that was like coming up like this and another one that was coming up like that were still perpendicular? I'm not so sure this would still work. So I said, okay, I'll show you. And so let's say we've got the vector C. I need a vector that's heading up at a 45-degree angle. So maybe, yeah, we can just go 2, 2. And then another one doesn't need to be the same length, just needs to be perpendicular. So maybe if I go, or negative 5, 5. I heard that one somewhere. Okay, do you see how with these two vectors, 2, 2 would put me like here somewhere, and then negative 5, 5 would put me up there. So vector D is definitely longer than vector C, but do you see how since they're both heading out at 45-degree angles, I'm still keeping this thing orthogonal. Or those two vectors, I'm still keeping them orthogonal then. So the dot product of these two vectors should then still technically come out to 0 because we know that they are orthogonal. So let's try that real quick, see if this still holds. So C dot D, 2 times negative 5 plus 2 times 5. Negative 10 plus 10. 0, right? So no matter what, if the two vectors are orthogonal or perpendicular, the dot product is going to be 0. Okay. Now, like I said, there are going to be some questions where I ask you, okay, tell me if the vectors are perpendicular, parallel, or neither. Okay. So we found a way to check for perpendicular. Let's do the dot product, see if it comes out to 0. If it doesn't come out to 0, the two vectors could be parallel. They could be just something else, neither. Okay. So parallel, we don't do a dot product because the dot product is not going to tell us anything about parallel vectors. But you can kind of just look at them and tell sometimes. So let's see, where am I at in the alphabet here? E. So let's say vector E is 3, negative 5, and vector F is those two vectors are parallel. How do I know those two vectors are parallel? Mm-hmm. Yeah, well, almost. E times negative 2. Okay. So, remember how we talked about yesterday that if you just take a vector and you multiply it by a scalar, it's going to lengthen that vector, right? You were gone, so just be quiet. Okay, so if you multiply by a scalar, it lengthens it, or it could make it shorter as well, okay, depending on what it is. So, if that's the case, though, if you have two vectors where one is just a scalar multiplication of the other one, shouldn't those two vectors be parallel then? They're sitting on top of each other. One's just longer or shorter than the other one. So that makes them parallel, okay? So F is the vector E times negative 2. So they're parallel. That's one way of looking at it. The other way that I think is kind of nice because it harks back to some things you guys have done in math class in the past, like in algebra. Think of a vector and its slope. What do we know about the slopes of lines that are parallel? They're the same. So if I can calculate a slope for each one of these vectors and they come out the same, then I've shown that they're parallel, okay? So the slope of E, okay, rise over run, y over x, negative 5 over 3. All right, the slope of F, it'd be 10 over negative 6. Both of these reduce to negative 5/3. Okay, so if you want a nice, neat way to show vectors are parallel, I think this is probably the best way to do it. It's just to calculate a slope for each individual vector and then check it out. Okay, so you can do this to check for parallel. You can do the dot product to check for orthogonal. And then if neither one of those two things check out, guess what? It's neither. It's not parallel. It's not perpendicular. Okay, so I'm going to give you guys a couple of vectors and I would like you to check. Are they parallel? Are they perpendicular? Are they neither? What's going on? So okay, so let's go negative 3, 6, and 12, negative 8. So check. Are they orthogonal, perpendicular? Are they parallel? Are they neither? and show your calculations, please. Right now. Carson, Tim. Right now.
You want to know why they're called orthogonal?
Why are they called orthogonal?
Orthogonal means meet at a right angle.
Ooh, did you look that up? Ah.
So does perpendicular.
Oh.
Is it a synonym?
Oh.
Why would
It was invented in the 15th century
Nice.
by Brunelleschi.
You know your art history.
Yeah, unfortunately. What?
What'd you say was invented in the 15th century?
Orthogonals.
We made them.
Well, the guy who does my art history says they're invented. So.
Don't tell anybody. Okay, so what do we got here? They're neither, right? Definitely not orthogonal. Doesn't come out to 0, comes out to negative 84. And they're also definitely not parallel because the two slopes are negative 2 and negative 2/3. Those are not the same thing. So these would be classified as neither. Okay, so there's one application of the dot product is this whole orthogonal business. But like I said, I will ask you to check for parallel and all that too because we can. So another application of a dot product is finding the angle between two vectors. Now, this process I'm about to show you, or this formula I'm about to show you, you technically don't have to use it. There is a way to find the angle between two vectors without using a dot product. Okay? So, let me quickly describe that for you, just so you guys know what we're talking about here. So let's say I've got this vector v, and I've got this vector w, and my goal, like I said, is to figure out the angle between them. So I want to know this, right? What's that angle that the two make? Anybody think of a way that I could figure that out without a protractor? Yeah. If I find the direction of v and I find the direction of w, I am, just because it's nice. What could I do with those two directions if I were able to figure those out? Just subtract them, okay? So, technically, you could do the inverse tangent of y over x for each, get the angles, and subtract them. Angle between two vectors, done, okay? I got no problem if you want to just do it that way, okay? Some people find that to be less work, less confusing. It's more conceptual. They can see it, what's going on. There is a formula involving a dot product that will get the job done too. So if you can remember the formula, all you got to do is plug in, done. For some people, they figure that's a little easier because then I don't have to go through all these extra steps. I can just plug all my numbers into this one little formula, calculate it on my calculator, done. Okay? So here's that formula. Cosine of theta, and theta would be referring to this theta here, the angle that's between the two vectors, is equal to, oops, I'm using v and w, so I better switch to that. So it would be the dot product of V and W divided by the magnitude of V times the magnitude of W. Or, if you like things all solved out for you, theta then would technically be the inverse cosine of this, right? All right, so this is pretty much what you're going to do if you're going to use this formula. Now, I would do all of this stuff first and then go take the inverse cosine of it instead of trying to plug everything in all at the same time. It makes things a lot easier if you just take care of what's in the parentheses first and then do your inverse cosine. Now, some drawbacks to this, though, like I said. You got to remember the formula, and you got to plug all of this stuff in there. You got to do a dot product. You have to find two magnitudes and plug those in as well. So there's some work there that you have to do. So, you know, it can be a little bit tricky. On the plus side, all this angle business, remember when we did the inverse tangent, we said sometimes you have to worry about what quadrant it's in and you might have to add 180 degrees depending on where you're at. This thing doesn't care. Doesn't matter. It'll always work. So you don't have to even think about that. So there's a plus for it. But you got to calculate a lot of stuff in the meantime too. So I don't know. Something to think about. Vectors versus numbers again. The dot product of V and W comes out to a number, right? We talked about that. The magnitude of a vector is that a number or a vector? It's just a number, right? It's the length of the vector. So it's a number from the dot product divided by a number times a number. So this is all a what? Number. It's just one big number that you get. Inverse cosine of a number gives you the angle, okay? So you're not getting caught with some vector in here, and how do I take the cosine of a vector? But you don't have to worry about that because everything in here calculates down to a number when we're all done, and then you can do the inverse cosine of that. So let's try it once. I'm going to do this example both ways. I'll do it using the formula, and we'll do it directly doing the inverse tangent stuff, so you can just kind of take a look and see what would you rather do. And I think that's going to probably take us up to the end of today. So no homework. Yeah.
Are you going to give us homework over break?
I don't know. It depends on how nice you are to me.
Who's going to do?
All right. So let's say these are our two vectors, and we would like to find the angle in between V and W, -2,5 and 8,1. So first method, I'm going to go with the formula. All right, so using that formula, I got to get the dot product first. So that would be -16 plus 5, so -11. Also need the magnitude of each. Okay, so this is usually how I do this, is I do each magnitude individually, do the dot product individually, and then I can start putting those numbers in. So magnitude, square root of -2 squared plus 5 squared. So first magnitude is 5.385, and then square root of 8 squared plus 1 squared, 8.062. All right, so then I'm going to do the inverse cosine of the dot product, -11, divided by 5.385 times 8.062, which is the inverse cosine of, what do we got? -11 divided by 5.385 times 8.062. All right, so the inverse cosine of negative 0.2534 is what I got. So that gives us an angle of 104.68. If I take it out 2 decimal places, degrees, about 105 is the angle between those two vectors. Okay, so that process makes sense using the formula. Find the dot product, find the magnitudes, just put them in, do the inverse cosine. Got it. All right, doing it using the inverse tangents method. So for this one, I need to get my angle for each one. So my first theta, let's do this one for V. So I'll do a little subscript V there so we can keep them straight. Would be the inverse tangent of y over x, so 5 over negative 2. So what does that get us? Inverse tangent, 5 divided by negative 2. Okay, that's negative 68.1, about negative 68.2. What quadrant am I supposed to be in with this vector? Negative 2, 5. Second quadrant. Negative 68.2, is that in the second quadrant? Got to add your 180, yep. So, plus 180 degrees, this is actually 111.8 degrees. Okay, that's for vector V. For your vector W, inverse tangent of 1 over 8. Gets you about 7.13, I guess, degrees. What quadrant is that vector supposed to be in? 1, 8. First quadrant, right? 7.13 degrees, are we good? Yeah. That's in the first quadrant, right? Okay. So, the difference between these two, so theta is going to be the bigger one minus the smaller one. So it's going to be 111.8 minus 7.13. So I got 104.67. So there's some rounding apparently that happened. But you get the idea though, right? It's coming out to the same thing essentially. So like I said, I will not be offended if you do not want to use the dot product to do this. If you felt like that method there was easier, go for it. Yeah?
Okay, so I did it without specifying anything or rounding anything and just one giant convoluted formula.
Okay.
And I got 107.
107?
Yes. If you want to take a look at the formula.
I'll take a look. Yeah, just 1 second. I'm going to stop my camera. So women do it. All right, here we go, guys. All right, so to kind of explain what a projection is, I want to give you guys an example here of how it's used and use that to kind of build things up. So let's say we've got a box that's laying on a table. And please don't come after me with what's the coefficient of friction and all that kind of crap. We're just talking in general, okay, Matt? Okay. All right, so we got this box here. It's on a table or something. And there's a rope attached to it, let's say. All right, and somebody is pulling said rope to pull the box, okay? Now, let's say that this box is really, really heavy, okay? When this person pulls, and we can think of the pull as like a vector going this way. When that person pulls, what direction is the box actually going to move, though? Just to the right, correct? Okay, so this vector that he's pulling at has a certain amount of force to it. Well, there's applied force and there is effective force. Applied force would be the pull, okay? Now the effective force is the portion of that force that is actually effective, that actually works on the box. And so
the force coming this way is the effective force. So if you know what the applied force is on an object, and you know what the angle is that they're pulling that applied force at, then you can use a projection to determine what the effective force is. Okay? So here's how it works. So I'll break this down without a box now. Okay, so let's say we got two vectors. This one up here is the applied force. We'll call this vector u. And then the effective force, well, we'll leave that one be for right now. But this is vector u from that picture above it. This vector right here, I'm going to call it w. Vector w is the, it's a directional vector. So it doesn't really matter how long it is, honestly. It just is showing you, it's just indicating the direction of movement that the effective force is going to have. So to figure out what that effective force actually is, we do a projection. And a projection is taking this vector, and it's kind of like the top vector is casting a shadow on the other one. So if I were to go straight down, perpendicular, from the tip of this vector down to vector w, then this vector, I'm going to make it a little thicker here. That vector right there is the effective force. And that effective force, like I said, is the projection of u onto w. Okay. The word projection makes sense in that situation. Think about, what does a projector do? Like shines light on something, right? So if you think of, like, you know, the sun's up here or whatever, and then you're casting the shadow of the vector, you're projecting the vector down onto the other one. That's kind of where that name comes from. Okay. Now, there's a formula for figuring out, like if you know, like I said, this vector u, and you know this vector w, there's a formula involving the dot product that allows you to get the projection. Okay, so it looks something like this. And I actually have a handout. I won't give it to you today because I'm sick, but I did a proof of this formula. It took me like the better part of a page, but I did it. But I'm not going to show it to you because I don't want to spend an entire page of notes just showing you that. So, but if you are interested later, by all means. All right, so it looks like that. And this notation right here, okay, that's just read the projection of u onto w. So the subscript, the little w there, okay, that's the vector that you're projecting onto. That's the directional vector. And then the big one in the notation there, that's the one that you're actually like doing the projection from in there. And so the formula for figuring out that projection then is the dot product of the two vectors divided by the length of the original vector squared times the directional vector. So
Wait, I thought you just said that W didn't have a length.
the length doesn't matter. That's what I said. I'll show you why in a minute. It doesn't matter. Here's the thing. W is a directional vector. The length of W does not matter, but the direction of W certainly does matter. That makes a difference, okay? So we'll get to that in just a second. I'll show you why. But so let's think about this for a second. The projection, yesterday we talked about how a dot product is just a number, right? And talked about when we were doing these calculations, when do we get a number, when do we get a vector? Is a projection a number or a vector? It's a vector, okay? Look at the picture, right? This is the projection, right? This vector is a projection. Well, let's look at the way we calculate that, see if that makes sense. U dot W. Dot product, that's just a number, right? Number divided by number, because the magnitude squared is just a number. So this whole parentheses here is just one big what? Number times W, which is a vector. A number times a vector is another vector, right? It's that scalar thing where you distribute into the vector. Then you got it? Okay. So, yeah, so that kind of verifies for us real quick. Okay, yeah, we are going to get a vector as an answer for these things, not a number. So the first thing that I want you to be able to do is, if I give you the component forms of these two vectors, can you do a projection of one onto the other, just to do the formula correctly? And then we'll start talking some application stuff, okay? So first, to verify that the length of W doesn't matter, I'm going to have you do two projections. I'm going to have that vector W being two different vectors that are in the same direction but a different length. So let's say the vector U is 5, 6, and vector W is 2, no, not 2, sorry. Let's go, I'm going to make this really big, so 24, we'll go 24, 2, okay. And let's find the projection of U onto W. All right, so we got to do the dot product of these two things. So I'm going to kind of come over here and just do that. So the dot product of U and W is 5 times 24 plus 6 times 2. That's going to be a pretty big number when we're down there, 100 and something. Plus 12. So 132, looks like. Okay, and then in the formula also we need the magnitude of W squared. Now here's kind of a nice thing. When you find the magnitude, you're always doing a big square root, right? Well, if I'm going to square a magnitude, I can do that with just the same way, just don't do the square root, right? Because it's just going to cancel it off. So the length of vector W would be, well, the length squared anyway, would be 24 squared plus 2 squared, which is also a very, very large number. 24 squared is 576, plus 4 is 580. Okay, so this projection then is going to be 132 over 580 times the vector W. So if I take this fraction and distribute it into there, that's going to be the projection then. So 132 over 580 times 24. So I'm getting 5.462, and then 132 over 580 times 2, and then I'm getting 0.455. All right, so that's my projection vector for that one. All right, now I'm going to have you guys repeat this process real quick. I'm going to pick another vector W. I'm going to have it be a different length than this one, but it's going to be parallel to it, in the same direction. And I'd like you to do this one on your own. Bless you.
In theory, should they all get smaller if you're doing a projection?
They could get longer.
They can.
Yeah, so like if I'm going to just quick jump down here for a second. But let's say this is your vector W. Here's your vector U. You can do a projection that way. It just comes down and it extends this one out then, and the projection is longer than W then. So that can happen, yeah. All right, so one that's parallel to 24.2. How about 12.1? Okay, so repeat what I just did with those two, okay? The answer should be exactly the same thing. Well, I already kind of told you that, so. But actually, like, practice doing the calculating part of it, though, so you've had that under your belt on your own. right, do we need any more time, or did we get that thing finished up? Did it end up being the same?
Yeah.
Yep, that should have come out the same. I'll unfreeze this and show you what I got for my work in case you didn't get there. So here's what I got. The dot product of these two vectors should be 66, and the magnitude of w squared, this w, should be 145. So it's 66 over 145 times that 12, 1 vector, which gets you exactly the same thing that we had there. Okay. So the length of that vector w doesn't matter, but notice I had to make these two things be parallel, though, so that they're in the same direction. Otherwise, they wouldn't necessarily come out the same then. All right, so that's how you perform a projection, doing the calculating part of it. So now let's actually try to apply it in a problem. So let's say, whoops, I don't want to go that high. It's the winter time. Your buddy is on a little sled.
Is it the winter time?
Yes, it is the winter time.
Isn't it winter time now? It's like snowboard.
Whatever, you can make it a snowboard if you want. All right, and so here's you standing up on the top of the hill. And there's a string attached to that thing.
Doesn't matter. I let it go and let it drop. I am Santa.
Yes, indeed. All right.
Maybe you're an elf.
Well, that could be too. You're kind of short, so elf would make sense. Oh, just kidding. All right, so let's say the hill is a 45-degree angle. Okay. And I want to know...
Wow.
So if your friend weighs 140 pounds, how much force is needed to keep them from falling? Now, you people that have taken physics, you've done probably stuff like this before. Not using projections, using some other stuff. So,
Question.
yes,
Going down the hill have to make more force.
it would make more acceleration. Force would be the same, though. Force is, mass times acceleration. Okay, so the force,
So he's not moving. We're assuming he's not moving.
he's standing
He's not
still.
falling down.
Exactly, all right. He is not accelerating. Right. Yeah, because that would change things, right? No, that's why there's the rope that you're holding him up at, not moving, so there's no increase in acceleration or anything like that. Actually, you know what? If he did go down the force, if he went down the hill, force would not increase because acceleration is constant due to gravity, right? So it's,
No, because you start out at 0 and you're going faster and faster, therefore you're accelerating.
no. You're accelerated.
Accelerate until you hit terminal velocity.
Force equals mass times acceleration, right?
Yes.
And acceleration due to gravity, even when you're standing still, is affecting you, right?
Yes.
Okay, so that acceleration is constant. It's always there.
See, but that doesn't make sense that you wouldn't need more force to pull it. I'm just from a logical
What's
standpoint, it wouldn't
easier
make
to
sense that
stop?
you wouldn't need more force to pull him up if he's going down the hill.
Yeah. I don't know. We're not going to worry about that, though.
No, he's not moving.
No, it's not.
And it's
I don't want to mess with that. I just want to get through this.
Is it a really, really icy hill then? So it's frictionless environment?
Yes, frictionless. Absolutely frictionless.
I'm taking away my sled.
Okay. So we're going to make some vectors for the sled, or for the guy's weight, and for the force, the effective force of you pulling on it. So him weighing 140 pounds, that's a force, right?
Are you pulling parallel to 45 degrees?
Yes.
Well, it looks like this.
Okay, yeah, well, just assume it's parallel. It's a good question. I understand. No, it's a good question. Anyway, so his weight, however, is straight down, right? Not parallel to the plane, but straight down towards the flat ground. So if he weighs 140 pounds, and that's like I said, a force, what would be a vector if it's straight down for his weight? What's the x component? 0. What's the y component? Nope. Negative 140. Right? His weight is going straight down. Now, the directional vector that we want to project onto, the effective force, is going to be parallel to the plane, though. Because that's the force, with the direction that you're pulling it at, that's the force needed to get him up. So that's the one that the length doesn't matter. Okay, that directional vector, who cares? So we'll call that one, I don't know, h, let's say. Okay, so a vector that is going up this plane, where I don't care how long it is, but it has to be 45 degrees. How might I construct that?
Just as long as the two numbers are the same.
As long as what two numbers are the same?
Coordinates. If it's like 2, 2, 3, 3.
Right. Exactly, because that ensures that you're at a 45-degree angle. Now, in case this angle were, let's say, something less convenient, like maybe it was 32 degrees or something, how might you do that, just so we can get that process down? Yeah?
Could you, like, pick a number and then use the sine and cosine of it?
Yeah. Yeah, exactly. So let's maybe do like 3. It doesn't matter. But so 3 cosine of 45, 3 sine of 45, something like that, okay? Now, the 45-degree angle, you're right. It's going to always come out the same, these two. But just in case you run across a problem where that's not the case, this will work. And I'm just going to put a little reminder on here. This can be anything.
Wait, why don't we just use 1 then?
If that floats your boat, go for it. I'm using 3.
1 is a lot simpler.
It's true, but yeah, think about it, man. 3. That's where it's at.
1, it doesn't change it.
Shut up and accept it.
And we're going with 3, man. All right, so we're going to change the mode here to degrees. Okay, so 3 cosine of 45. So I'm getting 2.121, and then I'll get the same thing for this one. Okay, so I want to project F onto H, correct? That's what we're going for, because H is the directional vector, F is the force that we want to project up onto it. So this one's kind of a weird one.
You're really doing it the hard way. I think we use coordinates 1, comma 1.
Yeah.
You could do that too. Anyway,
Any coordinates without multiplying them by...
No, you could just do any coordinates as
As long as,
as long as these are the same, it doesn't matter. Yeah, it doesn't matter.
you just do 3 comma 3 without multiplying them.
Sure. Yeah, but the reason I did the cosine and sine on this is because what if this wasn't 45?
Well, then you do that, but it is.
But then you could pick, as long as these two numbers were the same, you could do whatever, but you'd have to do the cosine of that angle and the sine of that angle. So I just put that on there just so you have a reference for other ones like that. Anywho, so you're projecting this is your F, okay, and then your H is kind of going up the hill like this. So your projection is actually projecting it down the other way, okay? So that projection vector is actually going to be the force that he's trying, that the weight of his sled and him are trying to push him down the hill, and you have this equal but opposite force you need to stop him from doing that. Okay, so the vector we're going to get, the projection is actually this little stubby one right here that's going down the inclined plane there. So we want to do projection of F onto H. Okay, so we need to do the dot product, which would be 0 plus negative 140 times 2.121. All right, so dot product is negative 296.94 with those two vectors. Magnitude of H squared. Now think about this for a second before you start using these decimals over here. What's the magnitude of H based on the way I made it? 3, right? Magnitude's 3, because that's the random number I chose to use with these two. So magnitude 3 squared, though, right? Magnitude squared, so this is 9. So the projection is going to be negative 296.94 over 9 times the vector h, 2.121, 2.121. So let's see what we get there. So times 2.121. Okay, so that vector, I'm getting two negative coordinates. Now look at my picture up there. Does that make sense why those are both negative? The vector is going in this direction, right? Which would imply third quadrant stuff, right? So that makes a bit of sense there. But to answer the question, I'm not quite there yet. I want to know how much force is needed to keep him from falling. And I got this as the vector required. Nope, you said it. Magnitude of that vector. How long is that vector, right? That's how much force you need to pull back on that thing. Yeah.
I don't understand where you got 3 squared.
The magnitude of this vector that I made up here, because I put the 3's up here in front of each one, that's the magnitude, right? That's where the magnitude goes when you do that, so I just stole that number. Otherwise, you could do the square root of this squared plus this squared, and you'd get 3. Okay. But, yeah. All right, so I need to take this, though, get its magnitude. So square root of negative 69.98 squared plus negative 69.98 squared. So let's see what we got there.
I have a question.
Yeah.
When I did it coordinates 1, 1, I got -69.5.
Mm-hmm.
Is that within acceptable leeway?
Let me see.
And that was without so when I used 1, 1.
You as your final answer, you got 69?
No, my coordinates are
Oh.
negative 69.5 instead of.
Oh, go ahead and do the magnitude. I'm pretty sure that'll be okay, though. I got about 99 pounds of force here. So 98.97 is what I got. But that should be relatively close.
98.3 pounds.
Yeah, I'll take it. That's okay. So, remember, pounds is a measure of force. So, if you pull back with about 99 pounds of force, you can keep your friend from sliding down the hill then. Okay, using a projection to do that. All right, I just realized there's one thing that I still got to talk about before I'm done. We got to talk about, sometimes. We got to talk about work. And you guys have probably seen this in science class before, or maybe not. Intro to physics, don't you guys talk about this?
I think so.
Anybody remember what work is?
No, and I don't want to.
Yeah, it's measured in like joules.
Joules or foot pounds or Newton meters. Work is a force over a distance. And in fact, more specifically, work is force multiplied by a distance. So that's why we get units for work that are like foot pounds, because pounds is a measure of force, feet is a measure of distance. So you just smash those two together, and that's the unit we use. The Newton meter, Newton is a measure of force, a meter is a measure of distance. So that's another commonly used one. Yeah?
That's why I don't like English and how it's worded, because you have to say force over a distance. It's not, but it's not force over distance. It's times distance.
Right, okay, yeah.
English doesn't translate.
So this is, this over is not like indicating the operation you do with the math. It's talking about over a distance that you travel, yeah. So, anywho, now, types of problems you guys have done probably in the past with this look something like this, and these are the really easy ones. How much force, how much work, not force, how much work is done. Pushing a box with 10 pounds of force a distance of 3 feet. Correct. No vectors needed, right? You just multiply the two numbers together. Work is force times the distance, right? There's your force, there's your distance. It's not hard. Yeah, now, we've been talking vectors. Now, here's the thing. As soon as you start looking at work, but the force is not a force that is just straight ahead, but the force being applied to the thing is in a different direction from whence it's actually moving, then things get tricky. Actually, we don't even need the projection. Nope. We can do a dot product with it, but looks like this. It becomes a dot product then. Work is force times a distance. Okay, and the force is a vector because the force is being applied in a certain direction, and the distance is a vector. Think of this now as this is the applied force again, okay, which is a vector in a certain direction with a certain length and all of that, and then the direction of which it moves is in a certain direction and all that. So the work done, we don't have to mess with the projection because we're not concerned about the effective force. We want to know how much work is done, and work is just multiplying those two things together. So just the force vector times the distance vector, which makes a number, which gives you a foot-pounds or Newton meters or whatever it is for your work. Yeah?
So if you had a question like the previous example where you're trying to keep it from moving, then your work is 0 every time.
Correct. I often do this example, and I'm not going to do. I can't touch any people today, so. That sounds bad, but what I would usually do is or maybe have 2 volunteers, but if you have somebody that is like holding somebody else up, you're exerting force to hold that person up off the ground, right? So you have a force, but how much work are you doing? None. Now, if you take that person and you bring them down and you squat them and bring them back up, are you doing work then? Yes, because you've moved them a distance and brought them back up. Okay, so that's the difference. There's always a force involved, and anytime there's a weight of something, because pounds is a measure of force. So there's always this force that's pulling this person to the ground, but until you move them, you're not actually doing any work, because the distance would be 0. Right, exactly. So, all right, so let's try this work using the vector way. So let's find the work done pushing a 10-pound box in the direction of 1, 2 over a distance of 3 feet from the point 0, 0 to 3, 0. Okay, so this 1, 2, this is referring to the force, referring to the force. You're pushing a 10-pound box in the direction of 1, 2, so that's the direction. This vector indicates the direction of that 10-pound force over a distance of 3 feet. So the direction it's actually moving when you apply that force goes from 0, 0 to 3, 0. So on a coordinate plane, what's actually happening is, okay, here's the object at 0, 0. Then it travels over to 3, 0. But the force you're applying it is from that vector, 1, 2. Okay, so we're going to use that to come up with our force vector, and then we've got a distance vector we're going to have to create here as well. So what is the magnitude of the force vector? 10. Okay, so actually let me start with that. So the magnitude of the force vector is 10. If I'm going to create a vector with a magnitude of 10 in the same direction as 1, 2, what do I need to know about 1, 2? Its angle, right? Same direction, I got to get its angle. So I got to do my inverse tangent, right? So that would be 2 over 1. So inverse tangent of 2 over 1 is 63.4 degrees. It's not 60.
I thought a 3069 triangle had.
It's
Like that was double.
the hypotenuse. The hypotenuse is twice the short leg, not the long leg, twice the short leg. So here's your angle. Here's your magnitude. So our force vector then for this would be 10 cosine of the angle, 63.4. 10 sine of the angle, 63.4. And so let's work that out real quick. So 10 cosine 63.4, 4.478 looks like. And then 10 sine of 63.4 is 8.942, I guess, yeah. Okay. So there's your force vector. We also need a vector for the distance, right? Well, look at the little graph that I made. See how it's going from 0, 0 to 3, 0? If I made this into a vector in standard position, what would be its component form? 3, 0, right? So I got to do the dot product of those two vectors. I got my work. Here's my foot-pounds. So we're going to get 3 times 4.478 plus 0 times 8.942. So we end up with 13.434 foot-pounds of work. All right, so it's that, like I said, that same equation that you would use, just multiplying the two things together. But if the force and the distance are both in different directions, we've got to make vectors for those. But then you just do the dot product. It turns into a dot product problem. And there's your answer. Okay, so feeling okay with this stuff? Think we can do it? Let's give it a try and see what happens. All right.